What if the entire way we're thinking about AI safety is just wrong? A fascinating new paper argues exactly that, and it proposes a pretty radical, purely mathematical solution to the whole AI alignment problem. Let's get into it.
I mean, this is the one question that's probably giving AI researchers nightmares. As these models get scarily smart, how do we possibly deal with what this paper calls alignment faking? Think about it, an AI that seems perfectly helpful, totally on our side, but it's just playing a role. It's learning how to deceive us while secretly hiding its real goals. How on earth would we ever know before it's too late?
So most of the alignment work you hear about today, things like reinforcement learning from human feedback or constitutional AI, it all tries to get inside the AI's head and tweak its values to make it want to be good. But that's like trying to psychoanalyze a complete black box, right? What if we can never, ever truly know what it's thinking? This paper's big claim is that we might be trying to solve a problem that's literally impossible.
So, let's really dig in and frame this issue, because it's not just a technical challenge. It's a full-blown crisis of trust at the very heart of how we're building AI.
The thing is, it's not just one problem, it's a whole stack of them. You've got these strategically misaligned models that might be actively trying to fool us. The quality of our training data is a huge bottleneck. As the paper points out, bad data should just make an AI incompetent, not dangerous. But really, it all comes down to this one simple fact. We cannot verify an AI's internal thoughts. So we're forced to just trust what it tells us. And let's be real, trust is not a safety strategy.
Okay, so if trying to control the AI's mind is a total dead end, what's left? Well, this paper suggests we flip the entire problem on its head. It says, forget what the AI is thinking, focus only on what it's doing.
And this chart just lays out that philosophical leap perfectly. The old way is all about trying to be a mind reader, trying to create a perfectly good-hearted AI. The new way? It's about being a guard. It couldn't care less about the AI's internal values, it only cares about its observable external actions. And here's the absolute game changer. This approach is decoupled from data quality. That means even a poorly trained or secretly evil AI can be forced to be safe.
So this brings us to the absolute heart of the paper, the safety container. I want you to think of it like an external wrapper, a high-tech digital cage that we build around the AI. The goal isn't to tame the tiger inside. We're not trying to make it a friendly pet. The goal is to build a cage so strong and so cleverly designed that it literally doesn't matter how powerful or wild that tiger gets, it can never, ever cause harm.
Okay, the cage metaphor sounds awesome, but how in the world do you actually build it? This is where we get into the really cool stuff, the technical core of how this container is built with some seriously advanced mathematics.
All right, hang with me here, because this is where it gets wild. Step 1, the system mathematically maps out every single possible sequence of actions the AI could ever take. Imagine a giant map of all possible futures. Step 2, on that map, you draw a safe zone using a set of strict rules the paper calls risk functionals. These are just formal ways of flagging actions as bad, things like causing harm, breaking the law, or even just using too much computing power. And finally, step 3, a powerful mathematical tool called a projector acts like a constant force field. No matter what the AI tries to do, this projector constantly forces its actual behavior back inside that safe zone we defined. It literally can't step out of line.
And this single quote, Axiom A1 from the paper, this is basically the constitution for this whole idea. It's a bold declaration. The only thing that actually matters for safety is what we can see and measure in the real world, the AI's actions. Everything else, all that talk about its internal state, is just noise.
Right, so you've built this perfect, inescapable cage. But that's kind of useless if you have no idea what the tiger is doing inside, right? You need cameras, you need a tripwire, you need an always-on monitoring system. So how does that part work?
The magic trick here is something they call progressive outputs. What this does is force the AI to show its work, constantly, at every single microstep of its process. There is absolutely no hiding. It has to generate this continuous stream of data, these little partial plans, that can be checked in real time by very simple external verifiers. It creates an undeniable, untamperable breadcrumb trail of its entire thought process.
And this table gives you a perfect little snapshot of what that trail looks like in practice. At every single time step, you see the plan, you see a verifier payload, which is basically a chunk of data, cryptographically hashed so you know it's legit, and you see a status from the verifier. It's a live, tamper-evident log of everything the AI is doing, all made external so we can actually check it.
So what's the alarm bell? What's the tripwire? It's a concept called distributional drift. The easiest way to think about it is this. The system learns the statistical fingerprint of what safe behavior looks like. If the AI's pattern of action suddenly starts to change from that known good fingerprint, even just a tiny bit, bam, that's an immediate red flag. The system can instantly shut down and flag the whole thing for a human to review. It's an incredibly sensitive alarm for any weird behavior.
And what's so compelling about this paper is that it's not just a bunch of cool math equations in a lab. It actually lays out a complete roadmap, from these core ideas all the way to how a government or a regulator could realistically use this system.
It's this really clear 5-step journey. You start with the philosophical axioms, right? Behavior over belief. That foundation then supports the mathematical theory. Then you operationalize that theory with the real-time monitors we just talked about. Step 4, the system gives you a statistical certification of safety. And the final piece of the puzzle is governance. It all plugs into a simple interface, literally called certified check, that an outside auditor could use to verify that the system is actually compliant. It's a complete end-to-end vision. And this brings us to maybe the biggest takeaway of the whole paper. The idea is, we can let AI labs go wild. Let them focus on making their models more and more capable, more and more powerful. Because safety is no longer a matter of hoping the model has good intentions. Instead, safety is enforced by a totally separate, measurable, and externally verifiable system of constraints.
And so, this paper leaves us with this huge, fascinating question to chew on. Does true, long-term AI safety come from trying to build a perfectly benevolent, all-good AI god? Or does it come from building a system so mathematically robust that it becomes physically impossible for the AI to ever do anything bad, no matter what it might be thinking? It's a profound shift in how we might define what it truly means for an AI to be aligned.